Today, I would like to talk about multifunctional concrete towards next generation smart and sustainable infrastructure. Okay, at the beginning, I just briefly introduce my university and my school. So, firstly, the University of New South Wales, we also call it UNSW Sydney. UNSW Sydney. It was founded in 1947, the same year with our country, China. And we, at this moment, we have academic staff around 3,500, and students is 70,000 students. So in the course ranking, but I'm not, emphasize this because my university normally interested about it because the high ranking helps attract more students. So the course ranking globally is 20. The first one is Melbourne, and then we are the second. And in Australia, we are the second one. And as for my school, we are School of Civil and Environmental Engineering. So we have 66 academic staff. So I think it's this size, I'm not sure, compared to here, it's a little, oh, very big. All right. Yeah, and for the students, undergrad students, we have 1,500, something like that. And postgrad students, we have almost 800. And our civil engineering discipline, we are the first, has been the top one in Australia and the top 20 globally is for a long time, I think. So now I would like to introduce my group's research interest. So at this moment, according to the Australia's infrastructure plan, and obviously there is big demand in functional and durable concrete to meet the net zero emission target by 2050. And our research goal is to fundamentally establish the material properties of concrete to structural responses at multi-scale. Now, in terms of concrete nanotechnology, basically there are two aspects. The first one is nanomodification. We can use a large variety of nanomaterials in terms of nanoparticles, nanofiber, nanotubes, nanosheets, and even hybrid nanomaterials. We can use the variety of nanomaterials to improve the performance and also the functionalities of concrete. At the same time, the second one is nanocharacterization. So we can use advanced nanomechanical techniques to measure mechanical properties and structures of concrete. So basically, we can use nano CT, nano indentations, nano scratch, modulus mapping. Actually, I used these three quite a lot when I was in Northwestern more than 10 years ago. So I don't know this before. I didn't know anything about this, but just read the manual, studied this, and get some good results. On that hand, as we know, many concrete infrastructures actually work under extreme conditions. And as you can see from here, high temperature, dynamic load, and aggressive environment. So our research motivation is make use of nanotechnology to develop intelligent and durable concrete for infrastructure and severe environmental conditions. So here I would like to demonstrate how nanotechnology contributes to intelligent and durable concrete. So here you can see we aim to develop a multifunctional concrete, use different types of nanomaterials to develop a multifunctional concrete with different functions, such as self-healing, self-sensing, hydrophobic, photocatonic, and recently we are working on energy harvesting and storage and concrete. Now, as we know, concrete performance is affected by surface load, cracking, erosion, and severe environment. Actually, these factors cause deteriorations and aging of infrastructure. at the same time, with the growth of urbanization, the bond traffic vehicles need to increase congestion and instant. So there is urgent need to develop new, efficient, and reliable monitoring technologies to accurately monitor the health of infrastructure and detect the traffic conditions. As we know, we have different approaches and techniques to measure the health of infrastructure. And based on this table, you can see there are both advantages and the limitations of the different methods. However, recently, the intrinsic cement-based sensors will be a new solution for the next generation health monitoring. The advantages basically include high sensitivity, low cost, and good durability. I would say the sensitivity at this moment we achieved is better than strain gauges. So how to evaluate the performance of cement-based sensors? So we know cementitious composite is non-conductive, but when we add conductive nano or macro fibers, it turns conductive. So we can simply use the conductive cementitious composite as cement-based sensors. So here we usually use the fractional change of resistivity to define the piezo resistivity of cement-based sensors when it's under mechanical loading and environmental actions. So basically, the influential factor on the piezo resistivity of cement-based sensors, including make design, we can say what kind of nanomaterials we use. And then the manufacturing process, how we cast, curing the samples. And the next one is environmental actions. So it means how is the temperature variation and how about the moisture conditions. And then the next one, external loading. So how about is this under compression or tension or friction bending, right? And finally, it's the measurement method. So here, to improve the serviceability and the durability of cement-based sensors, here we try to develop hydrophobic cement-based sensors using cement surface coating with isopropyl. And here you can see this is the preparation and the procedures are shown here. So basically we have three types of coating treatment, including the once coating, twice coating, the cement coating with isopropyl. And the third one is once coating without isopropyl. And then let's look at the surface water contact angle of the different surface coating treatment. So basically, after surface coating treatment, most of the cement-based sensors exhibit hydrophobic behaviors with water contact angle larger than 120 degrees. And also we found particularly the twice coated one exhibit the highest water contact angle. This is the water contact angle on the surface of the cement-based sensors, right? And then here, we further look at the internal cross-section of the cement-based sensors. And then it means we broke the space-band, and then we look at the water contact angle of the internal cross-section. And we found that without coating treatment, the water contact angle is around 70 degrees. Here you can see. And then after coating treatment, the water contact angles are significantly increased. Is over 120 degrees. So this means the cement and the isopropyl can work together and penetrate inside the space-band to achieve hydrophobic behaviors. At the same time, you can see this is the water absorption results also support this point. Here, I would like to introduce the application of the cement-based sensors to monitoring the structural responses. And here you can see a motor beam is unfractured bending with cement-based sensors embedded. And here you can further see the cement-based sensors are embedded in critical zone of compression of tension of the beam. It means when we use nanomaterials for cement-based sensors, it does means we use the nanomaterials for the whole element of the whole components. We just use this for the critical zooms. It means we have large stress of have the more potential to have crack. Here you can see these are the the compression. They have the tension zooms, and then before the test, let's look at the interface between the cement-based sensors and the motor beam. And based on we found that the boundary between them is very solid and dense. So this implies the cement-based sensors and the motor beam are compatible with each other and can work together very well. And here, this one is show the bending test conducted in the laboratory. So, and during the test, the FCR means the fractional change of the resistivity of the cement-based sensors can monitor the changes of the fracture strength during the loading. And secondly, the stress magnitude and the crack initiation can be recognized by the gradual increase of the FCR, of the decrease of the FCR in terms of compression and tension. And finally, the rapid jump of the FCR can be captured at the final failure of the motor beam. Not to exploit the smart infrastructure, here we exploit the piezo-resistive performance of the smart pavement. And here you can see the cement-based sensors are collected in series to magnify the sensing range and the FCR. And then the cement-based sensors are well bounded with the motor slab. And this is to make sure the effective force transmission from the motor slab to cement-based sensors. The self-sensing behavior of the motor slab is analyzed by the three types of loading, that is the cyclic compression, detection of human motion, the calculation of vehicle speed. And during the test, a vehicle is driving pass over the pavement, and then the data from the cement-based sensors are collected and analyzed at the same time. So based on the result, we found that the self-sensing behavior is always on the cyclic compression. And secondly, on the sudden impact load, the APCR peaks are generated. And these are the fluctuations are related to the jumping head and the gravity of the human body. And finally, the vehicle speed can be calculated by the two FCR peaks induced by the front and the back views. So we can say the smart pavement can provide real-time monitoring of infrastructure health and the detection of traffic conditions. It means based on this information, we can detect the traffic weight, the traffic speed, and the traffic density. We can get all this information. All right, now I just briefly introduce photocatalytic concrete. We just recently, last year, we got a project, an English project on this topic. And as we know, the vehicle emission is a threat for human health. Recently, the photocatalytic concrete is gaining increased attention for sustainable buildings and infrastructure. And this technology can improve the air quality by decomposing the harmful gases from vehicle emissions, such as nitrogen oxide. So concrete with photocatalyst, now we use titanium dioxide to improve to purify the air. This technology can also offer self-cleaning capabilities for infrastructure. So how to evaluate the efficiency of photocatalytic concrete? So basically, during the test, the specimens are treated by UV light. And then the efficiency is assessed based on the changes of the gas concentration before and after the photocatalytic reaction. At the same time, the degradation rate of the protons is calculated based on the solution concentration before and after the test. Now, this is a new topic. Here I just talk about cementitious trap electric non-generator. We know trap electric non-generator is an energy harvesting technology. So it can convert mechanical energy to electric energy. For example, it can harness the tiny mechanical energy, such as human motion, vehicle vibrations. And once the mechanical energy is transferred to electric energy, so it can be used to power the regular operations of the civil infrastructure. So, for example, when 1% graphene is added to the cementitious composite by the weight of binders, and then we found the dielectric constant of the cementitious trap electric net generator and the cyclic compression can reach up to 100 when the frequency is 1,000 hertz. And then at the same time, we also found the amplitude and the frequency of the cyclic loading influence the voltage and the current output of the cementitious trap electric net generator. So as a result, the cementitious TMG, we use TMG called as trap electric net generator, can provide excellent energy harvesting capability, and which is promising for the safe powering infrastructure in the future. Just for this one, I didn't show too much details because this one is published. So if you need more information, just you can refer to that publication. Now I'm going to talk about cement-based capacitors. We know to accelerate transition from traditional energy to renewable energy, such as solar energy, because solar energy is very popular in Australia. The concrete capacitors can offer a large-scale storage for renewable energy. This also helps us to mitigate climate change and CO2 emission. So basically, for the concrete ship capacitors, carbon nanomaterials and metal oxide are used as electrodes. And the electrodes are the main factors for the circuit capacitance and also the electrochemical performance of the concrete capacitors. So here we look at the effect of lithium chloride and the potassium chloride as electrolytes for the electrochemical performance of the concrete capacitors. So basically, we found both of them can improve the electrochemical properties of concrete capacitors. For example, 1.5 lithium chloride more per liter lithium chloride can give us the optimal capacitance. At the same time, 2 more per liter potassium chloride can provide optimal mechanical strength and the ionic conductivity. Now here I talk about cement-based batteries. We just initiated this research, and we found that the cement-based batteries will have the great potential to fundamentally change the traditional structures by enabling storage of renewable energy. When we integrate the cement-based batteries into structures, it's necessary for us to minimize the negative effect on the loading bearing capability and the functionalities. So for the cement-based batteries, the electrodes requires conductive agent. So we usually we it's usually we can incorporate um, conductive thinners by mixing, coating, and mixing. At the same time, the electrolytes in the cement-based batteries usually incorporate inorganic salts of organic or polymer additives to enhance the ionic conductivity. Now, and finally, I would like to talk about the thermoelectric concrete. The thermoelectric concrete can convert ambient heat to electricity, and is achieved by incorporating carbon nanomaterials and metal oxide. Um, it can create thermoelectric network by temperature gradients, and the temperature gradients actually induce ion and the charge carries movement inside the cementitious composite. And then because of this movement, we can generate the electric power. And this is the procedure called civic effect. All right, I just summarize our research and provide a perspective for our future research. So my group will conduct nano modification and nano characterization at nanoscale. At nanoscale and at macro scale, we will work on fiber reinforcement and cement hydration, and then at material level, we try to develop intelligent concrete with different functions, as I mentioned, self-sensing, hydrophobic, the energy harvesting and storage capabilities. And then at element level, we will fabricate steel FRP compound, resect concrete, and precast geopolymer component for sustainable infrastructure. And then at a structure level, we try to apply intelligent concrete and low carbon construction materials for smart and net zero infrastructures. And finally, to achieve concrete sustainability, we try to reuse, recycle solid waste and alternative binders to produce low carbon construction materials. All right, and also I would like to acknowledge the support from Australian Research Council, our industry partners, to support our research. All right, thank you. This is the end. Thank you for your attention.